Hi, mathematicians. I'm sorry if the video from yesterday was a pain in the butt. I realized that if I want it to fit on YouTube, I just have to make it a little bit shorter. So I think YouTube really works a little bit better for you seeing it. So I'm just going to have a timer going. So hopefully I can keep this closer to like a 13-minute video and a 7-minute video or something like that. So lesson 3 is building the perfect square. Or maybe I could just do it under 13, or 14. That would be sick. So you should pause it, obviously. You should try to graph each function. And then after you pause it and try, I'll go over the answers. So, hopefully you paused it. That one is going to go right and down. So maybe I want to see this section. Sorry, I'm just adding my axes. You could just keep trying yours. And this one is just going to go down. Okay, but we're going to have a kind of shift there. So let's put our axes there. Okay, so looking at the first one, remember our vertex form is y equals a times x minus h squared plus k. In this case, I've got no h, right? So my vertex is 0, 5. I'm not going to go left or right, but I am going to go up 5. And then my a value is equal to negative 1 in this problem. So instead of going over 1 up 1, I'm going to go over 1 down 1. Same thing to the left and the right. And then over 2 down 4. Left 2 down 4. And then right 3 down 9. And left 3 down 9. So we get a graph of a parabola like this. We can always use our calculator, right? I should be able to pull up this equation on my calculator and then look at the graph and see like, oh, okay, yeah, for sure I graphed this one right. Looking at number 2. Number 2 is going to be at 1, negative 3 as a point, right? So left 1, down 3. And then the a value in this case is still just 1, because if there's nothing in front of the parentheses, it's a sneaky 1. So from there, I'm just going to go over 1 up, 1 to the left and to the right. I don't know why I graphed it here. I guess I thought I was going down further and right further, but I'm not really. Then over 2 up 4. And then the last one would be over 3 up 9 to the left and the right, but I just don't have that on my graph. All right, last one, number 3. This one, we've got an h of 0 again, but a k of negative 5, because there's nothing in parentheses there. And our a this time is equal to positive 2. So if I go down here to negative 5, and then from there I'm doing slope counts of 2, so instead of going over 1 up 1, I'm going to go over 1 up 2. And then over 1 up 2 to the left and to the right. Same thing for my other problem. I wish I had shifted it down lower. That's okay. Just know that from there I'm going to go 2 times 4, which would have been 8. And that's going to be like right here. Just 1 square off the graph. I could have put my axes in better positions. Hopefully you will. Just thinking about showing enough of the points, right? I think usually on derivative you only need to have at least 3 or so points of the parabola, the vertex and the first couple on either side, and then it should graph it for you. So hopefully we feel okay about this jump start and our vertex form of our quadratic. So we're going to do finding the square of a binomial expression. So in terms of like our binomial expression, this is probably our double distribution maybe? The thing that makes me think that is the fact that I've got a square trinomial here, right? So going from like an x plus m times an x plus n squared. In this case, we could start probably ending up with some different side lengths. So maybe we're still sticking with perfect square areas. So maybe let's change that to the example that we had with a p, right? So this would be an x plus p times an x plus p. In terms of that double distribution, we're going to distribute this to both sides, so we get an x squared plus a px. We also get, when we distribute our other terms, sorry, that's one of my dogs. We've got a px and then a p squared. So then rewriting it as our trinomial was our x squared plus 2px plus p squared. And that was our equivalent to our standard form, which is ax squared plus bx plus c. Right? So when we're thinking about our trinomial, we're thinking about standard form. Our squared binomial is our square side length squared, and then when we expand it out, it looks like our area, because this is our length times our width. And then recognizing perfect square trinomials would be ones that come from this sort of pattern, right, where the square root of the p value doubled is our other value, right? So I should be able to work back and forth between my c in terms of b and my b in terms of c, right? If b is equal to 2p and c is equal to p squared, I should be able to kind of manipulate these numbers, right? So for example, in this problem, if I were to take the square root of both sides, I could turn that equation into the square root of c is equal to my p value. And if I know the b value, I should be able to manipulate that equation as well by dividing by 2 on both sides and recognizing that p would then be b cut in half. Right, so we should be able to either like take the square root if we have c, or take it and cut it in half if we have b, and then be able to figure out back to our side length, right? Because in this case, p has to do with our side length change, right? P is our side change to the square, whatever we're changing it by. Are we making the side bigger? Or are we making it smaller? That's how we can kind of think about creating our perfect squares. All right, rolling then into this lesson. Notice here we've got that quilting pattern. So if Optim uses 3 inches to the side of the square, and her original face of her robot for her robot quilt was that x squared, and then we added on these 3 additional inch pieces. This is our square pattern, and then our 3 times 3 are these 9 little squares in this corner, right? So using both the diagram and the equation to explain how these things work, this is the sum of all the parts. Right, so I think Derivative likes blue for the x squared, so there's the 1x squared. I think they use green for the x's, so we have 3 x's on this side, 3 x's on this side for a total of 6 x's. And then I think on Derivative they use yellow for these bottom squares, so there are 9 little yellow squares in the bottom. If I wanted to double distribute with this equation, the x plus 3 squared, I could write it as x plus 3 times x plus 3. That's our area, right, in this case. Oh, so they're using a of x, but you get the vibe. I could change it to a of x. In this case, then I could double distribute, get my x squared and my 3x, another 3x, and my 9, and the 3 plus 3 when I combine like terms gets me my 6x plus 9. So using 2 different ways to show how the area of the square works. So looking at, so we looked at the area of the square. I guess we could have gotten it by adding those all together, and then we verified it a couple ways. So for each of these following problems, you're drawing the quilts and then showing the 2 equivalent equations. The one equivalent equation, right, one is going to be standard form. And standard form is going to be our ax squared plus our bx plus our c. And that's just going to be the sum of the parts. Right, our x squareds being our squares, our bx's being our single x's, and our c's being our little ones. And then the other equation is going to be our vertex form, which comes from our a times x minus h squared plus k. In this way, this is going to be our side change. Our a is going to be our number of squares, like our x squareds, and then our k is going to be used to balance the ones. So, looking at this first one, so we can do number 3, and then maybe I'll have you do number 4, right? If I were to draw this picture, I've got my x squared, and then I've got to add 2 units on each side. Right, so here's my x plus 2, and then another x plus 2 on this side. Here's my x squared, here's an x and an x, so there's my x plus 2. Another x and another x, so my other x plus 2. 2 times 2 gets me my 4 little ones down here in this corner. If I add up all the parts, I've got a 1x squared, I've got 4 x's, and I've got the 4 little ones. So that's my sum of my parts. Right, this is my squares, big squares. These are my rectangles. And these are my ones, my little squares. And then just verifying that with our double distribution, right? If I did an x plus 2 squared, that would be x plus 2 times x plus 2. And then when I double distribute, I get my x squared plus my 2x, another 2x, and a 4. And when I combine like the terms, I get my x squared plus my 4x plus 4. So there are number 3's answers. You should try number 4 on your own and then answer number 5. What kind of patterns do you notice between like the diagrams and the equations and different things? We're coming up on the end of the video link that I can upload to YouTube, so I'm just going to stop there and then I'll make a second video for the rest of the lesson.